I did get emailed a question from section 2.7, so we'll go ahead and look at that together. The questions that I assign you from Wiley are usually just short answer or multiple choice. That's because otherwise you would have to sit and type in the answers, and all your answers wouldn't match the person's next to you, so I'd have to go through and grade them all. And since I have more than 90 students most semesters, I don't want to do that. But you can certainly go check on the other Mindscapes yourself if you'd like to get into more in-depth questions. So I'd gotten emailed a question about number 8 because it says find a rational number that is bigger than these two numbers, bigger than this number but smaller than this number. I just wanted to point out to you all that there are in fact 3 answers. So it says find a number, but you're supposed to find 3 numbers, okay? Does anybody have any questions? Okay. Then we'll continue on in 2.7. We've been looking at rational numbers and irrational numbers, but we never figured out why rational numbers have the decimal expansion that they do. So we'll continue on in 2.7 and we'll answer the question, why do rational numbers decimal expansions terminate or end in a repeating decimal? Why do rational numbers' decimal expansions terminate or end in a repeating decimal pattern? So you'll need a full page for this, and this is your class activity, so make sure you get a piece of paper out and work along with me here, because what we're going to do is look at a rational numbers' decimal expansion. We're going to look at 45 divided by 7. For 9 decimal places. So we take 45 and divide it by 7 using long division for 9 decimal places. Who remembers how to do long division? What number do we pick here? Pick 6, right? Because 7 goes into 45 6 times, and then you take the 6 and you say 6 times 7. 6 times 7 is 42, and you write the 42 here, and then you subtract. So we pick 6 because 6 times 7 is 42, and then we subtract. 45 minus 42 is 3. Now what do we do?
Do you bring a 0 down?
Yep, you bring a 0 down. So we need to bring a 0 down so we remember that 45 can be written as 45.0 repeating, and that's how we're going to think of 45. We put the decimal place above, right next to the 6 as well. Then we can bring down zeros as many times as we want, which is about 9 times. Okay, so 7 goes into 34 times because 4 times 7 is 28. So write down 28 and subtract. 30 minus 28 is 2. So we'll bring down another 0. 7 goes into 22 times. 2 times 7 is 14. So we can go ahead and subtract. 20 minus 14 is 6. We'll bring down another 0. 7 goes into 68 times. 8 times 7 is 56. Go ahead and subtract. 60 minus 56 is 4. Bring down another 0. 7 goes into 45 times, because 5 times 7 is 35. 40 minus 35 is 5. So we bring down another 0. 7 goes into 57 times. 7 times 7 is 49. We subtract. Aren't you glad they invented calculators? Yeah. 50 minus 49 is 1. We bring down the 0. 7 goes into 10. Oops, the computer froze here. Free it up. 7 goes into 10 one time. 1 times 7 is 7, and we'll subtract. 10 minus 7 is 3. So bring down a 0. 7 goes into 30 4 times. 4 times 7 is 28. We must be getting pretty close here, right? 1, 2, 3, 4, 5, 6, 7. A couple more times here. 30 minus 28 is 2. I'll bring down another 0. 7 goes into 20 2 times. 2 times 7 is 14, and we subtract and get 6. Bring down another 0. 60 divided by 7, we can choose 8 now, because 8 times 7 is 56. When we subtract, we have 4. How long could we keep doing this? I mean, we're stopping at 9, but that's kind of arbitrary. How long could we keep doing this?
Forever.
Yeah, forever. This will go on forever. Can you see what the pattern is? Good. 428571 is repeating, because now we have the 428, and next would come 571 again. So 45 divided by 7 is 6.428571, with the 428571 repeating over and over again. Now that we've done this, why must the 45 over 7 either terminate? How would we know if it had terminated? Yes.
We wouldn't be able to divide anymore?
We wouldn't be able to divide anymore. And how come? Did you have your hand up too?
Mm-hmm.
How come we wouldn't be able to divide anymore?
Because there wouldn't be anything else to divide with.
There wouldn't be anything else to divide with. Because what would we have gotten?
0.
Yeah, 0. We'd have gotten a 0. A remainder would have been 0 because we wouldn't have had anything left to divide with. Okay, but instead it's repeating. Did anybody see why it's repeating? The math panned out that way. Well, why did the math pan out that way? Yes. Because we started with a fraction, so we knew this was going to happen. The rational number will repeat itself. So what is it about being a fraction that makes it repeat itself? Let's look at the remainders. Let's look at possible remainders. Okay, we could have got 0. Then it could have just terminated. Or we could have gotten 1 or 2 or 3 or 4 or 5 or 6. Could I have had a remainder of 7? No, not a remainder of 7. Why couldn't I have had a remainder of 7 or 8 or 9 or anything?
So it would have been able to be divisible again.
Good, because I wouldn't have done it right the first time. It could have had more taken out. It could have been divided again. Okay, so these are the only choices. for the remainder. So when we got to, let's see, when did we pick times 4? Right here. When our remainder was a 3, then we started having the same pattern again, right? You're just bringing down zeros, so when your remainder is a 3, now you're dividing into 30. And we did that once before, so the whole arithmetic's going to, as you said, pan out the same exact way. Well, we learned a principle that tells us that this repeating is going to happen. Does anybody know the principle we learned in chapter 2 that's telling us that this repeating is going to happen, not in section 2.7 where we discussed rational numbers, but in an earlier section where we talked about if you only have 1, 2, 3, 4, 5, 6, 7 possible remainders and we're going for 9 decimal places. Yes? Good. Good. The pigeonhole principle. The pigeonhole principle tells us that if we're going to take and do long division and there's only 7 possible remainders and we're going for 9 decimal places, one of those decimal places has to be repeated. And once we start repeating, well, then you're going to have the same math follow through over and over again. So that's why rational numbers have decimal expansions that terminate and in 0, or you could think of it as 0 repeating forever, or have a repeating decimal expansion. Because of the pigeonhole principle, we're going to just start. We're going to hit a number we hit before for a remainder, and from that point on, it's the same. We're going to also talk, this is your class activity. So go ahead and take your camera out, please, and take a picture of this. And you should upload it right away if you can, because we're going to do another class activity later on, and that way they won't get mixed up. So if you can, yes, good idea. Thank you. Good reminder. Put your placard in there and get your class activity uploaded. So we'll get it right in the 2.7 Dropbox or assignment, and that way when we upload the next one, it won't get mixed up. Then we're going to continue talking about the density of the real numbers. The real numbers are dense. Now, dense has a number of different meanings. Do you ever call somebody dense? That's probably not a polite thing to say, right? So I don't mean dense like that. I mean that the real numbers are thick. There's always another real number between two real numbers. Let's look and see how that works out. Let's look at 0.1 and 0.2. And let's examine those as a visual. So let's take our circle here and divide it up into tenths. Does anybody ever do that with pizza? You get like Papa Murphy's pizza and it says the calories per 1/10 of the pizza, so then you're like, I got to divide it up into tenths pretty equally here, but I'm still going to try and get the biggest tenth. Yeah. So we have our tenths, and we have 1/10. So each of these represents a tenth. And we have 1/10 or we have 2/10, and we need something in between. Of course, you can find something in between. We're doing this with decimals, and so I'll divide one of the tenths up even more into tenths. So then I'll divide one of the tenths up into hundredths. So I'm going to do this with pencil because I don't think this is going to come out very neatly. Hopefully you're better at this than me, but dividing up into 10 again. Okay, so pretend these are all even. When someone asks you for just a sliver of pizza, this is what they mean, okay? Okay. So we have hundredths now. So I can find the number between 0.1 and 0.2 by just taking 0.1 and adding on one more decimal place, right? So whenever we add a successive decimal place, we're adding a tiny bit more than what we had with the decimal before it. We're adding a piece that's 1/10 as big as the decimal before it. So if I added another decimal, or even like 3 other decimals, then I'd be saying I want 3 more quantities that are each 1/10 as big as these hundredths. So if I could divide these little 1/100ths into 10 each and took 3 of them, I'd be getting 0.113. Now, you notice I still don't get up to 0.2 though, right? Even if I'm adding on a third decimal place, I don't get up to 0.2 in size. This 0.2 would be both of these. So when I say the real numbers are dense, I'm saying that between any 2 real numbers, there's more real numbers. In fact, how many real numbers are between 0.1 and 0.2? Yes. Yeah, there's an infinite number of numbers in between 0.1 and 0.2. So infinite numbers fall between 0.1 and 0.2, and those could be infinite real numbers that are rational or infinite real numbers that are irrational. So I have the 2 rational numbers listed, 0.11 and 0.113, but I could have put 0.1, 1, 2, 3, 4, 5, 6, ... for an example of a irrational number. In fact, let's go ahead and fill that out more so we're clear that it does not repeat at all. Okay, so there's an example of an irrational number that falls between 0.1 and 0.2. So the real numbers are dense. You can always squeeze another real number between any 2 real numbers you have because of the way we can write their decimal expansion is just adding a tiny bit more when we put another digit there. Now that explains why the Pythagoreans were so flabbergasted when they could not express the square root of 2 as a fraction. They couldn't express the square root of 2 as a rational number because you can see you can make rational numbers so detailed and so tiny. It seems like you should be able to express any quantity in terms of just a rational number that terminates or has a repeating pattern at the end, but we found that we were not, in fact, able to do that, and there are irrational numbers. So now that we've given some more thought to the rational numbers, I have the question for 2.7 for you to talk about. In fact, let's write this question down. This is the author's question. I didn't give it to you before because I wanted you to think about these a lot. So let's write it down and think about it together. Is there a number between 0.999 ... and 1? Is there a number between 0.999 ... and 1? So I'm going to ask you to answer that yes, no, and impossible to determine. So you could pick one of those answers. I'd like you to talk about it in groups and see what you come up with, okay? And then we'll meet together and talk about it. So I'll help you find a group if you're not in a group. Yes. Okay, so you two are in a group. Are you three?
Or just do
all in a group?
one.
And are you two? Can you come up and try to keep around and try to
Yeah.
Are you two working together?
I would say it's an technically,
I might your message first. I'll get it.
it's not one, but you might want not.
And if I don't
But
wake
the
up,
thing is, it just keeps going.
I don't know.
I'll eventually wake up. I'll leave my phone on vibrate and I'll put it next to me so it shouldn't shake.
Just like how
Yeah, I don't think you can. Oh, one or one?
Oh, that's not even, half time races is on actually screen.
You good?
Is it-
You're good? You got stuck on it.
Right, to learn, just remember.
This is how would you write 0.99999 repeating as a fraction?
You would say equal to 10, right?
This is decimal expansion.
Yeah. But 10 because it repeats in the 10.
I think, yeah, because the 9 should keep going on forever. Even if you tried like
So it is,
stack,
there is a
you
number.
rounded 1, it would only round
I'll go ahead
next
and
to
leave the decimal expansion so
0,
you can-
which wouldn't round all of them.
So you're saying that there is a number? Are you saying there is? Which one are you circling?
Yes.
Okay, then you're assigning us to figure out what the number is. Okay.
Right? And I said equal to that.
What we just talked about?
Keep it 9 and equals 9.
So it doesn't matter.
What did your group decide?
9 over 9, which
No,
is 1.
there's nothing in between? Because you couldn't find out what would it be. What did your group decide?
You said yes.
Yes. There is something in between.
Yeah.
And your assignment is to figure out what it is.
Okay.
Okay.
There you go.
There you go.
Well, this is indeed a tricky question. In fact, won't it make a good topic for dinner this evening? I'm going out with some of the math people here in our department. I'll ask them what they think. Let's see what they remember. All right, so I heard all different answers. One group went to figure out what this is as a fraction, right? Did one group do that? Yeah. Okay, let's do that. Let's take 0.999 and write it as a fraction. It's a rational number. We can see that because the decimal expansion repeats. So we name it n. We all know how to do this now from taking and studying for the quiz. Then what do we multiply n times? 10. Yeah, one digit repeating, so multiply by 10 with 1 0 there. So 10. So the decimal place moves 1 to the right, 9.999 dot dot dot. And then we'll line up the 1n underneath it and subtract. So you have 9n equals, now these 9s are all lining up, so they all subtract except 9 to the left of the decimal doesn't subtract. So 9n equals 9. We'll just divide both sides of the equation by 9 now. Did you get n is 1? Good. What does that mean? These are the same, right? That's what it means. It means 1 has 2 names. 1 is 1, and 1 is also equal to 0.99999 with no with the decimal never ending. So 1 has 2 names. There is no number between 0.9999 and 1, which if you tried to search for it, you would have found, wait a minute, what could it possibly be? Because there's no number there. These are just 2 names for the same number. So sometimes students think, well, this is the number next to 1. There is no number next to 1. There is no number next to any number. You can always fit another number in between. There is no number next to another. But this particular number, 0.99999, is in fact the same as 1. So some of the interesting aspects of the way that we work our decimal system. Let's go ahead and go on to section 3.1. Does anybody have questions before we do that? Yes, that was the class activities.
So there's 2 class activities. So do I always put we're getting to the next one?
So this is the class activity for 2.7, and we will have one in 3.1 also. Okay. Any other questions? So chapter 3 is about infinity. Infinity brought a lot of dissension among the math community in the 1880s. It's not even clear that infinity belongs in the math community. Should it be a philosophical idea or a religious idea? Maybe it's a idea that belongs in literature. So where does infinity belong? Your author says it's one of the great successes of the human intellect to take this vast idea and tame it and make it susceptible to reason. Well, when I mentioned infinity to you, I imagine something came to mind, so I'd like you to write down what came to mind when you heard the word infinity. So just whatever came into your head, can you write that down? And then I'll ask a few of you to share it. I can see what came into some of your heads. Some of you thought this is going to go on forever. No, tell me what you thought. What, do you want to share? No. Okay, who wants to share? What did you think? Yes.
Nothing mathematical, but just the quote, infinity and beyond.
Oh, sure. Infinity and beyond. That's good. Anything else? Anybody else have ideas that came to mind? Yeah. Yes.
My mind went straight to the book, The Fault in Our Stars.
What is it called?
The Fault in Our Stars.
Well, how do you spell that?
F-A-U-L-T and then
F-A-U.
in Our Stars.
And is there an E in there?
No, it's in as in I-N.
Oh, The Fault in Our Stars?
Yeah.
Oh! Is this good? I should read this?
10 out of 10.
Yes.
Oh, good to know.
Read it, watch the movie.
Cry.
Cry. It is the best movie.
Okay, well, I'm glad to know that. I'm always looking for more good books. Anybody else have other things come to mind? Yes.
I don't know if this makes sense, but the universe, because it's always growing.
The universe, because it's always growing. So definitely a vast idea. So we are going to be talking about infinity in chapter 3. In 3.1 though, we start small. Okay, we're going to understand simple things deeply by starting with the finite. So we're going to look at some examples of finite sets. What are some examples of finite sets? So mathematicians use little braces like this. They're on your keyboard, kind of next to the letter P. Okay. So we use these braces to read the set of. The set of markers in the classroom. That would be an example of a finite set. I could go through and see there's probably about 15. Or how about the people in this room? So the set of people in this room, that's a finite set, not a very large set. Or how about the pencils in this room? That would be a finite collection or a finite set. So a set is just a collection of elements, a collection of items. Well, we want to make it up to infinity, so we're going to start comparing the sizes of sets. Comparing the sizes of sets. But we're not going to do it by counting. So we're going to compare the sizes of sets, but not by counting. We're going to, well, let's think about a way to do it. Let's think about the shoes in the classroom. So the set of shoes in the classroom and the set of feet in the classroom. So I want to compare the sizes of these sets and see which one's larger. But I'm going to do it without counting. So I'll check. Is anyone barefoot? Not usually in Wisconsin in the winter, but maybe. Is anyone barefoot? Okay. How about, does anyone have an extra pair of shoes in your backpack or with you? Sometimes people bring extra shoes to wear to the gym. Okay, so no one's barefoot. So it looks like we have the same number of shoes as we have feet. Okay, is that good? So we matched them up, same size. How about cell phones? Let's take a look at the number of people in class and the set of cell phones in the room here. Now I don't bring a phone to class, so I don't have a phone. But maybe somebody else has more than one phone. Sometimes people have an extra phone, maybe for work or something. Does anybody have more than one phone? Anybody in class have more than one phone? No. Nobody brought more than one phone. So since I don't have a phone, then we can say that the set of people in the class is larger than the set of cell phones in the class. So you see how we're pairing them up? We're pairing up to compare sizes of sets. We're not counting, we're pairing up. How about the number of shoes in class and the number of socks in class? So sometimes people don't wear socks, especially if you have sandals. Does anybody not have socks on? Okay. Sometimes people have extra socks. I take extra socks to the gym. Anybody have extra pair of socks with them? Okay. So we can say these are the same size sets as well. So what we're doing when we're pairing up like this is we're creating a one-to-one correspondence. A one-to-one correspondence, or a pairing, a one-to-one pairing, where the elements can be paired evenly. The elements are paired evenly. We just match them up. There's no extra. Each is matched. Each is matched with another one. So I'm going to give you some sets now, and I'm going to ask you to decide if there's a one-to-one correspondence between the sets or not. And sometimes I'll say correspondence, and sometimes I'll say pairing. We can use those ideas interchangeably. So here's a few sets to think about. Is there a one-to-one correspondence Is there a one-to-one correspondence between, and then we'll have several questions, okay? So the first question, students in the classroom. Okay, one set will be the students in the classroom, and one set will be noses in the classroom. Students in class, in this classroom, and the noses in class. I'll give you a couple of these to look at, okay? So another one will be people in class, so in this classroom, and faces in the classroom. So we have the people in the classroom and the faces in the classroom for a second example that you can decide if there's a one-to-one correspondence or not. And then we'll have feet in the classroom and people in the classroom. So go through A, B, and C and decide, is there a one-to-one correspondence between the two sets in each case, please? Okay, and by the way, these are all good quiz questions too, okay? So, for A, what did you decide? Is there a one-to-one correspondence between the faces in the classroom, the students in the classroom and the noses in the classroom?
No.
Is there somebody with an extra nose or no nose?
You said students.
Oh, good job! Good job. Good job. So no, because I have a nose. The teacher has a nose.
Mm-hmm.
Did anybody else catch that? I have it written in my notes, but I completely forgot it. Okay. How about B? People in the class and faces in the class. What's that one? Yes. Yes, there is a one-to-one correspondence. How about feet in the class and people in the class? No, because most people have 2 feet. Okay. So when we look at a one-to-one correspondence, what your author does and what I'll be doing to try and remind you over and over is to look at the fingers on your hands, okay? So there's a one-to-one correspondence between the fingers on my right hand and my fingers on my left hand. They can each have one matching the other. Line them up. None are missed, none are used twice. Okay. Now, we were looking for a one-to-one correspondence in the last set of questions. Now we're going to actually make a one-to-one correspondence. We're going to make a one-to-one correspondence. So remember, we're doing all of this with finite sets because we're going to move on into the infinite, and we want to have finite down really solid so we can extend the ideas into the infinite without getting confused. So we'll have two examples here as well. We'll have a set with the numbers 1, 2, 3, 4, and 5. And then another set, we'll write right underneath it A, B, C, D, and E. And we'll make a one-to-one correspondence. So the way we indicate a one-to-one correspondence is with a double-sided arrow. So I'm going to assign the 1 to go with A, the 2 to go with B, the 3 to go with C, the 4 to go with D, and the 5 to go with E. So that's how I'm indicating that each element in the first set is assigned exactly one element in the second set. None are used twice. Everyone is used. So the double-sided arrow is just a way to assign. Now, you wouldn't have to have the one with the A. Oh, thank you. You wouldn't have to have the one with the A. You could put the 1 with the E and the 5 with the A, or mix it up however you want. It's just a little easier to follow the arrows if they are straight up and down. Let's try another example. I'm going to make a one-to-one correspondence to make a one-to-one correspondence if possible. If possible. So here I'll have the set 1, 2, 3, 4, 5 again. And then I'll have another set with the days of the week. So Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. So in the example A, we were able to have one element in the first set to go exactly with one element in the second set. But in B, we cannot. There's not a one-to-one correspondence there because there's more elements in the second set than there are in the first set. So it's impossible to make a one-to-one correspondence or a one-to-one pairing. So if I wanted to take a look at these two sets of toothpicks, okay, I could tell if they were the same size collection of toothpicks by taking them out one at a time, right? Pairing them up, pairing them up, pairing them up. And if there was some left over in one set and not in the other, then I'd know that one set was bigger. So that's what we're doing here. In fact, the main point of 3.1 is right here. Two sets are exactly the same size. Two sets are exactly the same size if and only if and only if their elements can be put into a one-to-one pairing. Into a one-to-one pairing, or I'll put in parentheses correspondence. A one-to-one correspondence would be the same thing. So two sets are exactly the same size if and only if their elements, oops, I spelled there wrong. Let's fix that. if and only if their elements can be put into a one-to-one pairing or one-to-one correspondence. So I'd like you all to stand up. Everybody stand up. Okay, stand up. Okay, put your right hand on your heart, raise your left hand, and read it off the screen with me, okay? Really, nice and loud, okay? Okay, two sets, come on, two sets are exactly the same size if and only if their elements can be put into a one-to-one pairing, so help my God. Okay, okay, thank you.
Well.
So I want you to be very serious about that because in the math community in the 1800s, there was some severe infighting, really hurt feelings. Some people even went into insane asylums from talking over this idea. Okay, so we don't want anyone to feel like that. We want you to have all solid feeling on that. Okay, this is 3.1 class activity, this statement. How do you tell if two sets are the same size? Okay, so if you have any questions, see me after class. Have a wonderful weekend. Yep, this statement that you swore to.
I wrote it in French.
I can't read French, so maybe Jordan translate it for me. Okay, thank you.
What's the homework on one of the last